who is Tang Kai instead of Wu Zhibo. He will talk about the progress of laser time transfer at the Chinese space station. He will join us online. Can if you are ready, please.
Hello. Hello, can you hear me? Hello.
We can hear you. I think you have to play your presentation by yourself.
Did I share my presentation?
Yes, we see that.
Okay. Hello, Wu Zhibo. He cannot attend this meeting, so he had to let me take his place, if I could. I am Tang Kai from Shanghai Astronomical Observatory. Welcome to this presentation on progress of laser time transfer on China Space Station. An overview of today's presentation. First, I'm going to talk about the background and the project current situation. Then something detailed about the payload. Moving on to the third part, it is about dedicated ground SLR station. The last part, I'll conclude with summary and expectations. China Space Station has been under construction all the time. The core module and the laboratory module 1 have been successfully sent to the outer space in April 2021 and July 2022, respectively. Laser time transfer LTT payload as a part of high precision time frequency system is on laboratory module 2, which was just launched in the past week. The whole experiment system includes a hydrogen atomic clock, a cooled atom microwave clock, and a strontium optical clock. And there are 2 time frequency transfer links, laser link and microwave link. This is an outline of the operation scenario of the LTT experiment. Its main purpose is to perform a time comparison between clocks on the ground and the clocks in space. The whole link contains ground segment and onboard segment. The ground part is actually an SLR station connected with a precise clock. The onboard part includes laser ranging retroreflectors, detectors, and timers. From SLR ranges, one can precisely compute the time of arrival of the laser pulse at the location of the reflector on satellite with respect to the timescale of the SLR system on the ground, which provides the relation between the timescale on the ground and timescale on satellite. This payload was required to meet a standard of time deviation of 0.1 picosecond at 300 seconds and 1 picosecond at 1 day. The orbit altitude is about 400 kilometers, what makes passing time very short. That is also why we need a pyramid LRA and optics with a large field of view. The LTT payload operates with the grain laser. It supports laser pulse repetition of 1 or 2 or 10 kilohertz. As I said, the detection unit of payload has a big field of view of more than 120 degrees, or 14 to 60 incidents, corresponding to 20 to 85 degrees of tracking elevation. Onboard detector precision is 25 picosecond, while the precision of timer is about 8 picosecond. The frequency reference is 200 megahertz from optical comb. The gate signal is synchronized with 1 PPS generated by GNSS. The LRA reflectors is a small pyramid with 4 CCRs, each of which has a clear aperture of 33 millimeter. There are two SIM detectors to back up for each other. The LRA and the detectors are installed on the SIM structure to keep their position relationship stable. The payload has 3 circuit boards inside. They are detector and timer circuit, interface circuit, and the power circuit. The whole payload weighs about 6 kilograms, and the power consumption is about 24 watt, with fluctuations up and down according to different working mode. The payload is temperature controlled through liquid cooling. Detector chips is K14 spot of 100 micrometers by Czech Technology University. In order to achieve the better stability, we find laws of delay and precision changed with counting rate through measurement. The recommended counting rate is 5 to 20%, approaching single 14 level. The detector used the avalanche voltage compensated circuit and fine adjustment of resistance circuit to lower the temperature drift. We finally managed to set it to a level of 0.1 picosecond per Kelvin. Speaking of optics, as European laser time transfer payload is a good precedent, we actually partly borrows from it. It consists of a snowflake attenuator, a PTFE scatter, pinholes, and filter. The materials of scatter we chose has the advantage that its relative transmittance of different laser incident angle changes less than that of ground glass. Also, it has better shock resistance. The snowflake gives a selective attenuation dependent of incidence. Along with scatter, it helps maintain counting rate of detector stable. The narrow bandpass filter is of 4 nanometer in full width at half maximum for spectral filtering. Pinholes inside reduce noise light from multiple internal reflections. Considering scatter attenuator and laser radar equation, the relative change of photons that hit the detector target plane reached 25%. The relative change can be defined as the ratio of the minimum to the maximum. The onboard timer is set to event time record mode using FPGA and TDC. The repetition rate is up to 20 kHz. To minimize the timer's internal delay change, we used a 2-channel compensation. And time stability is better than 40 femtosecond in short time and 100 femtosecond in long term. The LRA is pyramid shaped, just like the classic one on CHAMP. The active reflecting area stays more than 30% of maximum within field of view of 120 degrees, fitting in with the detectors. Over the past year, we developed an electronical module, qualification module, and a flight module. These are the pictures of them and the pictures about a series of tests. The flight module was put to the measurement in laboratory. The payload and the whole test system got a precision of around 22 picosecond at a rate of 7%. The time stability reached 0.09 picosecond at 300 seconds and less than 0.8 picosecond at 1 day. The flight module of the payload was just launched on October 31st, the past week. The picture on the right side shows the payload on orbit. The picture was taken by a panorama camera on the space station. The space station is now being tested, and experiments is expected to be conducted in the next year, if everything is going to be all right. There are 2 dedicated ground stations that are under construction in China. A removable one is built in Xi'an, and another fixed one is in Beijing. For both stations, the receiving telescope is 40 centimeter, and the laser is 10 kilohertz, 0.4 millijoule per pulse. The laser divergence is less than 10 arcsecond. Since the gauge signal on board is synchronized with GNSS, laser pulse transmitting time will be adjustable with a precision of 10 nanosecond. By applying continuously adjustable attenuators to transmitting and receiving optics, we expect to reduce the influence from time walk effect of the detectors. To achieve more stable working environment, both stations is designed with a tracking dome, and the optical box will have temperature controller inside. Besides the fixed calibration target, telescopes also have calibration targets attached, so they can calibrate system delay while tracking. We hope it helps. Here's the conclusion. Laser time transfer payload on China space station has been developed and launched. After months of preparation on orbit, there will be opportunities to carry out the experiment. The payload has been measured at lab. The result turned to be reached all the goals. And more stations and more ideas are welcome to do experiment with laser time transfer payload on China space station. That's all for the presentation. Thank you.
I think we are running out of time. Just a short, quick question, please.
At first, congratulations to putting this into orbit. This looks very promising, also with respect to the features that you have shown. Do you plan to allow for collaboration with other ILRS stations and to share the data that the onboard detector is receiving?
Yes, the payload is open for. I believe it's open for all the stations who are willing to join the observation.
Okay, and what was the inclination of the space station again? The orbiter inclination? Could you please say what was the orbital inclination of the Chinese space station again?
The orbit inclination. I'm not quite sure, but it may be 40.
40-degree elevation, roughly?
43 degree,
okay,
maybe.
Yeah. And a very short last question, sorry. How long can you operate this strontium optical clock on board the station continuously?
I didn't quite follow you.
You said there is a strontium optical clock on board the Chinese space station. How long are you capable of operating this continuously?
We made the tracking no more than 200 seconds, I believe. Sometimes
you maybe translate briefly? Wang, can you do me the favor of translating my question?
In Chinese?
Yes, thank you.
I think we are heavily over time now, so I will translate this question between you two. Yeah, we'll do it later. And also we get some questions online, but we have really no time. And